Okay, now I want to take a look at using the convolution table. Um, the convolution table contains a small list of convolution pairs, but there are some algebraic, we'll call them tricks, that you can play to greatly extend the usefulness of the convolution table. So, for example, let's take a look at the problem we just worked, where x of t is equal to u of t and h of t is equal to u of t plus 2 minus u of t minus 2. Again, I can't find this directly in the table, but I can use my convolution properties. I can write y of t, x of t convolved with h of t. Convolution is distributed across a sum or difference, so I can write y of t is equal to u of t convolved with u of t plus 2 minus u of t convolved with u of t minus 2. Okay. And again, neither one of these is directly in my table, but what is in my table is u of t convolved with u of t. So let me call that w of t, and from the convolution table I see that that's equal to t u of t. Okay. And then from another convolution property, it's this shifting property. So knowing this, I know that u of t convolved with u of t plus 2 is going to just be a shifted form of u of t convolved with u of t. And it's going to be shifted 2 units to the left, so I just replace t with t plus 2. And so I know I'm going to get this result. And then similarly for the other part here, u of t convolved with u of t minus 2. Shifting either one of these functions shifts the output by the same amount. If both functions are shifted, I have to shift the output by the total shift. So in this case, t minus 2, u of t minus 2, and then so I get then combining these two, the output is t plus 2 u of t plus 2 minus t minus 2 u of t minus 2. And this is the same result that we got previously for this case, but a little simpler using the convolution table. Let's take a look at another example. This is similar to example 2 from this lecture, but I'll make it a little more difficult. Okay. Previously we had h of t was just e to the minus t u of t, but I'm going to make this e to the minus t u of t minus 2. This is actually a shifted function. It doesn't start until it doesn't become non-zero until t is greater than 2, but it's not just a simple shifted version of e to the minus t u of t. Okay, I can rewrite it in a form so that it is a shifted version of a function that's in our convolution table. I mean, we can find in our convolution table the result of x of t equal u of t, and let me call it h1 of t is equal to e to the minus t u of t minus u of t. Again, this convolution pair is in our table, and h of t is not just a simple shifted version of h1 of t, but I can do a little algebra though and write h of t is, I've got a t minus 2 here, and the argument of the u of t, I need to get a t of t minus 2 here. So I'll do a little algebra trick. E to the minus, I'll write t minus 2 plus 2. Again, that's just adding 0. U of t minus 2. And I can pull this e to the minus 2 term out. That's just a constant using the properties of exponentials. And this is e to the minus t minus 2, u of t minus 2. Okay. And then now I see, by comparing h of t and h1 of t, that h of t is simply related to h1 of t. It's e to the minus 2, this constant, and then this is h1 of t shifted 2 units to the right. So h of t is e to the minus 2 times h1 of t minus 2. Okay. And so I know the result from my convolution table. I know x of t convolved with h1 of t is 1 minus e to the minus t u of t. And so I know two things going on here when I look at the relationship between h of t and h1 of t. There's this multiplication by a scalar, but convolution is a linear process, so that's just going to multiply the output by e to the minus 2. And then h of t is a shifted version of h1 of t. It's shifted to the right by 2, so everywhere that t appears, I substitute t minus 2, and I get this result then for the output. Okay, I can actually pull out an e to the plus 2 out of, or actually multiply this e to the minus 2 through to write that a little more simply as e to the minus 2 minus, here I'll have e to the minus 2 plus 2 e to the minus t u of t minus 2. And the output doesn't start until t equal 2 seconds, but my input starts at 0, but my impulse response doesn't start until t equal 2 seconds. Again, it's shifted to the right. So this is a response due to an impulse at the origin. My input starts at the origin, but the output is actually delayed by 2 seconds. So you can use tricks like this not only with exponential functions, but also with sinusoidal functions to incorporate a time shift actually as a phase shift, and then use the convolution table to find the result of convolution. And you have to be a little careful. Let me take a look at one other example. Let's take a look at x of t equals u of t, and h of t is e to the minus t minus 2 u of t. Okay. And this is not a time-shifted function, actually. It starts at t equal to 0. And in fact, I can rewrite this using the properties of exponentials as e to the second power times e to the minus t u of t. And then, so now I can find this convolution pair directly in my convolution table. Or at least I can find u of t times e to the minus t u of t, and then this is just multiplied by e to the second power. So the result would be e squared. The rest of this is in my convolution table. Again, there's no time shift here. If I look at the input, it's a unit step. It looks like this, okay, with all t, and the impulse response, h of t, would be, again, it's 0 for all t less than 0 due to the unit step. At t equal to 0, it's actually, it would be e squared. So that's the only difference. It starts at e to the second power instead of starting at 1, and then is a decaying exponential. And then the output also would start at t equal to 2. T equal to 0. The output would look something like this. At t equal to 0, it is 0. Again, it's continuous. It's 0 for t less than 0. And then it's going to build up actually to approach e squared here as t becomes large. So this is what the output looks like for a system that has this impulse response in response to a unit step.